So yeah, so I'm going to talk about solving still wait the ball. Diophantine equations. Okay. Using elliptic curves. So this is a very old story, okay. And so we all know how Wiles was inspired to solve the to prove that the Fermat equation does not have any non-trivial solutions. So let's begin with what we have to do. So first of all, I would like to just recall a few things. I think yesterday Somnath would have told you what modular forms are. Okay, so I'm going to give you a working definition of what a new form is. Okay, so this is only a working definition. Okay. All right. So working definition. This is of a new form. Of a new form. So a new form is a modular form. All right. So new form. F is a modular form, okay? And a modular form has, yeah, so a modular form is an elliptic function, f of z plus 1 equals f of z, right? So it has a Fourier series expansion, yeah. Yeah. So f is said to be a modular form, okay, if f of az plus b divided by this is equal to or k here, right? Okay, where a, b, c, d, so this belongs to and z is an element in the upper half plane. Okay, so this is the upper half plane. Right? So you can put here, say a is equal to 1, b is equal to 1, c equal to 0, and d is equal to 1. Right, then you get your f of z, right? So it's periodic function, so it will have a Fourier series expansion, right? And if the Fourier series expansion, okay, it starts from, yeah, so f of, so f z plus 1 equals f of z, and so you will have a Fourier series expansion. You make the transformation, z maps to e to the power 2 pi I z. Okay, then you can write, I can write as f of q, so maybe f of, doesn't matter, this is equal to summation c n q to the power n bigger than or equal to 0 here, right? And f is called a Cusy form, so f is called Cusy form. If your a0 is equal to 0. Okay, so this is only a working definition. You have to prove each of these things. So these are what modular forms are, but sometimes what you want to do is that you don't want the whole of SL2Z. You want only some special subgroups of SL2Z, okay? So for example, you can have subgroups which are known as gamma naught of n. So this is all those A, B, C, D inside SL2Z. Okay, such that your C is congruent to 0 mod n. And if you want this for these kinds of subgroups, you say that your F is a cusp form of level n. Okay, so then cusp form of level n. Okay, and what is a new form? So for a new form, so I have the space of all the cusp forms, so let me denote them by, so S, K, N, okay? So this will be the space of all cusp forms of weight K. So this number K that appears here is called the weight of weight K, and level is n. All right. So this is the okay. This is going to be a vector space defined over the set of complex numbers, and there are you know what the dimension is depending upon n. Okay, so this is a number which you can, there's a formula you plug in, and then you know what a dimension is. Okay? Yeah. Any questions? Yeah. So f of z is summation c and q to the n. I see. Yeah, so this would be C0 equal to C0. So, and there are operators which are acting on this space, okay, which are known as Hecke operators. There are operators acting on this, which are known as Hecke operators. Okay. Yeah, and this is a finite dimensional vector space over C, and these Hecke operators act on this, yeah, and you can have some of these functions which are eigenvalues for all the Hecke operators. Okay, they are known as eigenforms. Okay, so cusp forms which are eigenvectors for all Hecke operators. Okay, so these are known as eigenforms. Okay. Yeah. So suppose, for example, if this space is one-dimensional, then of course it has, yeah, it will have one eigenform. For example, you know that, so S12 and then 1, if I take, yeah, level 1, right? So this is dimension 1, dimension over C, so this is equal to 1. This is generated by your Ramanujan's delta function. Okay, so this is the first primeval example due to Ramanujan. Yeah, and so sometimes what can happen is that even if your form F is a cusp form of level n, okay, if you look close enough, then you find that actually it's coming from its actual level. You can lower down the level, okay, to say some number which is a divisor of n. If that doesn't happen, you call this cusp form, eigenform, to be a new form, okay? So F is a new form if the level n is minimal, okay, in a sense that F does not arise from anything, from any level which is lower than n, okay? So then in that case, you say F is a new form. Okay, but what is more important is that, okay, so this is important for us, is that the theorem due to Shimura, that if I have a new form and if I have F equals summation, say, Cn q to the power n, then all these Cn's they're algebraic integers, okay? So new form of any level or any way, new form, then Cn's are algebraic integers, okay? They belong to Q bar. Q equals or 2 pi I z, okay? So this is it. Sorry? Yes. Yeah, so if, no, it's not exactly multiplicative, but multiplicative means that, say, C PQ is the same as CP times CQ, if P and Q are co-prime. Some relations are there. Are you talking about that? Huh? Level n is minimal here. The level n is minimal. So it means that F can actually arise from F is actually, can be an element of SKM where m divides n. Yes, that's there, but I'm just giving you a working definition of, so it doesn't, it's genuinely of level n. It doesn't arise from anything which is of level, less than n, all right? It can arise from level m and dividing n. Okay, so this does not happen. And you say that F is a primitive, okay? Okay, so, but you can forget everything and remember only this part, okay? New form means that there is a power series expansion where the Cn's are algebraic integers and you somehow know how to calculate them, okay? So that's the only thing that you have to remember. And yeah, so maybe I'll write here. No, I can't erase this. Yeah, so Somnath has a point. What he's saying is, I think I forgot to mention this. So here, so your C1 is equal to 1. Okay, so you have to normalize. U form by definition is actually normalized. It's normalized. Okay, if you have any coefficients coming from Q, coefficient of Q, then you have to divide that out. Otherwise, it's not. can't talk about it. All right? Okay, so the other thing is that if you adjoin, so this is the second fact, you adjoin all the Ci's, say C2, C3, and so on, all the Fourier coefficients to Q, then this is actually a finite extension, finite extension of Q. So it's a number field. Okay? And you know that if you take Cn, right? So this is big O of n to the power of k minus 1 by 2, right? And if k equals 2, then Cn or C, say let's say L, less than or equal to 2 to the power L. Okay, so this is known. This is called the Hasse bound for the Fourier coefficients. And so, in fact, more is true. Like, if you have one f like that, since this is a finite and totally real extension of Q, you can put an automorphism of this, take an automorphism of this and apply it on f. That will also give me another new form. Okay, so they will all satisfy this inequality if the weight is 2. Clear? Okay, so now let me state the theorem. Okay. So theorem is that this is due to Wiles, and Taylor-Wilo. It says that if I have an elliptic curve, okay, so if I have an elliptic curve E over Q, this is an elliptic curve. Okay, and the elliptic curve has something called the conductor, right? So it has been defined of conductor N. Okay, then there exists a rational form. Rational form means where all its real coefficients are rational numbers. Rational form F. Okay, so this is actually a new form F of level n and weight 2. Okay, so that CL equals AL of E, right? This number, you know, AL of E is 1 plus L minus the number of points in a finite field FL, right? So this is except for finite many else. Okay, yeah, so this is the theorem, and the converse is also true. The converse was known much before Wiles. So it's actually a theorem due to Shimura that if you have a rational new form F of weight 2, then to that you can associate an elliptic curve, okay, of conductor N. You have to look at the what you call the Jacobian of the modular curve and the quotients of it. So now, okay, so remark, if F is rational new form of weight 2, then there exists an elliptic curve E defined over Q, okay, such that your F, so that CL is equal to AL of E, okay, so for almost all primes. Okay, so this is due to Shimura. Yeah. So yeah. For almost all but finitely many. Yeah. So almost all means all but finitely many. Okay. So you have to. The exception consists of all the primes that divide the level of F. Okay. So now we talk about congruences between elliptic curves and modular forms in terms of the associated Galois representations. So this is one definition. Suppose I have an elliptic curve, so E over Q is an elliptic curve of conductor N, conductor equals to N, and F is Q plus summation Cn, Q to the power N, N bigger than or equal to 2, is another new form. Say of level, some level n prime. So then we say that E, the curve E arises. The curve E arises modulo P. P is a prime number, okay? Modulo P from a new form F. Be careful, huh? So new form F, if there exists some prime, okay, some prime ideal P, okay, so this is big P, dividing P, and this P is in this field here. There you have to look at the ring of integers of this. Okay, such that so this congruence is ALE is congruent to CL modulo P. Okay, so again I use the word here for almost all. So almost all means all but finitely many. Okay, so this will do wonder for us. Okay, this almost all thing. So okay. And if you find that's a thing, then you write. So this is the notation. Is E okay? And then you have a wave here, and then E, right? So you write like this, which means that the Fourier the ALEs, okay, and the CLs, they're congruent to each other modulo this prime for almost. This is of, yeah, for the time being, I'm sticking to any weight, I mean, okay? But, yeah, I mean, this is just the definition which says about, you know, congruence between Fourier coefficients. So, okay, so we make this more precise. Okay, so, so this is more precisely. Yeah, you can also stick to weight 2. It's okay, no problem. You can also stick to weight 2. So more precisely, the first one is if L does not divide P times N prime, then you have ALE is congruent to CL mod P, and if so L does not divide P times N prime, but L divides N only once, okay? Then L plus 1 is congruent to plus minus CL mod P. So this plus minus is coming from whether it has got split multiplicative or non-split multiplicative reduction. Yeah, except finally many. It doesn't, those primes that do not divide the conductor of E as well as F. So almost all prime means this one. So for all primes away from, you know, okay, so now, so even if I have written here a Cusy form, I can very well say E is congruent to another elliptic curve F, or capital F, big F, okay, then such a thing should be true. Okay, so using Shimura's theorem. Okay, so now one more last thing. Yeah, so I did.
Maybe somewhere you can write down the definition of ALE.
ALE, yeah, so recall that, so you recall that AL of E equals 1 plus L minus number of points of E FL, right? So this is if your L is a prime of good reduction, right? And then it's 1 if L is a prime of split multiplicative reduction, and then minus 1 if L is a prime of non-split multiplicative reduction, and then 0 if L is a prime of additive reduction. Okay, so remember this. This is all that is needed for this whole talk. Okay. So now, there is a very nice theorem due to Ribet. Okay, and I'm going to tell you this. Before that, let me just recall for you all these invariants. So I have, so you recall that associated to E, okay, so this is an elliptic curve. You have the discriminant, right? So this is the discriminant of E, okay? But then, see, when you say E over Q in elliptic curve, it's very nice, but it's very easy. But it actually has an explicit equation, right? You can compute the discriminant in terms of the coefficients of the elliptic curve, right? But there is one minimal, the smallest discriminant possible, okay, among all the models. Okay, and that's called the minimal discriminant. So delta min is nothing but the minimal discriminant. I mean, it is the discriminant of the minimal model of minimal Weierstrass model of E. Okay, so there is a well-known algorithm due to Tate to find out if you're given any model of the elliptic curve. There is an algorithm due to Tate. Okay, it's well implemented in Sage and Magma and so on to compute this delta min and also compute the precise equation of the elliptic curve. Okay, but we don't have the time to do that. And N is the conductor of E. So the same algorithm also computes the conductor of the elliptic curve. The conductor of the elliptic curve and the minimal discriminant have the same primes. It's just the power that differs. Okay? Yeah, so because you have L dividing N here, so it's either multiplicative or split multiplicative. So you have L plus 1 there. What was the question? Why do you have L plus 1 here? Yeah, so it comes from the fact whether it has L, whether L is a prime or split multiplicative or non-split multiplicative, but I forgot now. I'll just take 2 minutes to, yeah. Yeah, yeah. Okay. So, and you also compute, so this is for a fixed prime P, okay? So this is equal to N divided by all primes Q. Okay, so let me write it down here because this is very, very important number, this NP. So NP is equal to N divided by, so Q, and then P to order of Q. Okay, so now, from now on, so here I choose, we suppose we take delta equal to delta min, by which I mean that we're always looking at the minimal Weierstrass model of the elliptic curve. Okay, so now let me state this very nice theorem due to Ribet. It's called the level lowering theorem of Ribet. Okay, so again right here. Theorem. Ribet says that, so let E be an elliptic curve over Q, and E is a prime bigger than or equal to 5, okay, prime. Then suppose E does not have, okay, any P isogenous, right? So isogeny is an endomorphism from E to itself, okay, of degree. Any P isogenous, and then let NP be as above, like this NP. B is above, okay. Then there exists a new form F, okay, of level NP such that my E is congruent to F modulo P. Okay, so visibly you can see that NP it may happen that is less than n. Of course, I mean, this can still be 1, but the level of NP is less than or equal to the level, the conductor of the elliptic curve N, the conductor of the elliptic curve E. That's why this is called the level lowering theorem, okay? Just to Ribet, okay? But here, you need one critical assumption, which is that your E has to be a modular elliptic curve. Yeah, so associated to E, there has to be a modular form. Okay, so that's why the theorem of Wiles is needed for this statement to hold. The theorem of Wiles, which we wrote somewhere, is needed. Okay, modularity is needed for this theorem. Okay, so now, so I have this condition that E does not have any P isogenies. Now let me give you a few statements, okay? How to check this that doesn't have any P isogenies. Okay, so this is a theorem due to Mazin. You can look up the Eisenstein ideal paper of Mazin for this. Okay, so E over Q, again as before, is an elliptic curve, and such that at least one of the holes, at least one of the following. All right, then, okay, so let's say P bigger than or equal to 17, and the J invariant of the elliptic curve, okay, does not belong to J halved. Okay, third is that P is bigger than or equal to 11, and E is semi-stable. Okay, semi-stable means the conductor of the elliptic curve, okay, the primes that occur in the conductor, there are no powers. I mean, there is at most 2, yeah? And third is that P greater than or equal to 5, and the number of 2 torsion points on the elliptic curve is the maximum one is 4, okay, and E is semi-stable. Then E does not have any P isogenies. So the mode P reduction of the Galois representation that is associated to the dead module of the elliptic curve is irreducible. That's what it says. Okay, so now let's try to prove Fermat's last theorem. Okay, why is it? Yeah. Product of all primes Q, which occur like only at most once, and it should also be that P divides this. This is the order of this is the power of Q that appears in the order of in the discriminant. The order of the valuation, yeah. The order, the power of Q that appears. Okay, so now, okay, so let's try to solve this Diophantine equation. So this theorem of Ribet, okay, you can read it in this paper called Shimura-Taniyama plus epsilon implies Fermat. Okay, this is a strange name, implies Fermat. So it's the epsilon part. So he believes that this theorem is so small, this result is so small that he calls it epsilon, this level lowering condition. Okay, but as I said, modularity is needed, which is the crucial ingredient here. Okay, so let's try to prove this, that this does not have any equation for mass. Last theorem, this is due to Wiles. All right, so suppose P bigger than or equal to 5 is a prime, then the equation x to the p plus y to the p plus z to the p equals to 0. Okay, let's give a name here, number here, has no solutions x, y, z not equal to 0, right? So this is the theorem. So let's try to prove this. So yeah, so if I put here, or yeah, maybe I can also, yeah, so you might think that you put here 1, you put here -1, but then your z is 0. So this is the only trivial solution. So, okay, so you start with, so this is an idea due to Frey, okay? Okay, so I just write here like this. So what it says is that, suppose you start by assuming that your x, y, z is not equal to 0. Very nice. Okay, then, so this has a solution, right? So now you can assume that you can knock off the common, factors of, yes, and then you can assume that they are all pairwise coprime, right? So suppose if these two have a common factor, then that common factor is certainly going to divide z to the p, right? So I can assume that they're all pairwise coprime, right? Then, so without loss of generality, I can assume that x, y, z are coprime. And you can see that if these two are odd, if this is odd and this is odd, then this is going to be even, right? So one of them is going to be even. If this is even, then this is also even, right? So one of them is certainly going to be even. And one of them is even, say, y, right? So therefore, x to the p plus z to the p. My p is bigger than or equal to 5, so there will be a 4 appearing here at least, right? So if I go mod 4, then this will vanish, and then I will be left out with x to the p plus z to the p. So this is congruent to 0 mod 4, right? So, right? And I'm assuming that there was coprime, so it can't be even, this can't be even also because this is already even, right? So let's say that, so either this is congruent to +1 -1, and this is congruent to +1 -1. If this is congruent to +1, then it's congruent to -1 mod 4. And if this is congruent to -1, then this is congruent to 1 mod 4, right? So let's make an assumption. So let x to the p be congruent to -1 mod 4, and z to the p be congruent to 1 mod 4. Okay, so now I have to use this, right? X, y, z not equal to 0, and I also have to use, this, I have to make an elliptic curve out of this. Okay, so now associate to x, y, z, the solution, okay, the Frey curve. So this Frey curve so is E, which is given by y squared equals x times x minus x to the p, and then x plus y to the p. Okay? So you make this elliptic. This is an elliptic curve, by the way. Okay? So these are going to be the roots of this. Okay? They are going to give the two torsion points of the elliptic curve. They all lie right? They will all lie on the x-axis. Okay? Y is equal to 0 there, so they are torsion points. Then I compute the discriminant. So the discriminant of this, of the elliptic curve, is nothing but the discriminant of the cubic on this side times 16, right? Remember, always remember that, right? So you should not forget the 16, otherwise you run into problems. So 16 times x to the 2p, y to the 2p, x to the p, plus y to the p whole square, right? So this is the discriminant of this cubic, and I have multiplied by 16, and this is 16 times 2p, y to the 2p, and z to the 2p here. And you also remember this invariant C4. Has it been defined? I don't know, maybe this is not needed here to show z to the 2p minus. You can look up the notes of Sudhanshu and Sujata for this number. And the GCD of C4 and delta 16. Now, I apply my algorithm here, okay? And then, what do I get? Okay, so I run Tet's algorithm on this, okay? So applying Tet's algorithm. This algorithm is one of the Antwerp volumes, okay? That's algorithm. So we get delta mean 2 to the minus 8 or 2p, and n to be the product of all the primes L that divide x, y, and z. Right? And NP is equal to n divided by something here, and you finally get this to be, right? And if you take particularly, so N2 is 2. Okay, so you just compute this, and okay, now I have to also ensure this the non-existence of p isogenes. Okay, so let's do that. I will use one of these criterion. Okay. Which delta? Okay. All right, so now, further, EQ, the rational points, the two torsion points is equal to 4, as I said before, right? So the number, yeah, so they will be given by x to the p0, y to the p0, 0, 0, okay? And n is square free. Free, so therefore, so Mazur's theorem, n is square free means that your E is a semi-stable elliptic curve. Okay, so Mazur's theorem now implies that E yeah, has no p isogenes. Okay, so so therefore, by Ribet's level lowering theorem, there exists a new form f of just 1 second, okay, I think this is NP. Okay, there exists a new form of level NP equals 2 such that E is congruent to F mod P. Okay, so there exists a new form of level NP equal to 2 of weight 2. Okay, new form F of weight 2 level 2. So now what you do is that you just go back to your tables, but there is a there is a formula to compute the dimension. Okay, so however, the dimension, okay, there are no modular forms, there are no cusp forms of weight 2 level 2. Okay, so weight 2 level 2, there are no cusp forms at all. So that's a problem, right? So so this is a contradiction. We have arrived at a contradiction. Why is it a contradiction? It's because I know that my elliptic curve E is modular, so that elliptic curve actually works for this congruence to happen, but I'm saying that there does not exist any one of them. So this is a contradiction, which arises from the fact that I have such an elliptic curve. Okay, so this is a problem, so that's why, so therefore, no non-trivial solutions to okay, so this is the epsilon part from using the epsilon part. Okay, so yeah, so there is I have forgotten the dimension formula. Yeah. So there are no cusp forms of weight 2 level 2. Is it not 2 divided by 12? 2 divided by 12. The dimension formula for something like this, right? I don't remember it, but okay. So this is how you prove that this does not. I mean, there are no non-trivial solutions. Okay. So let's use this technique again to solve some more equations which are slightly more complicated than the Fermat equation. We are just pushing how we can use the level lowering theorem to prove that solutions do not exist. Okay, so what are we doing here? Okay, so I have Diophantine equation. And to this, I associate an elliptic curve. Okay, so this is usually known as a Frey curve. Okay, and I show that, well, I want to show that, so I construct an elliptic curve out of this, and I show that by using Ribet's level lowering theorem, I showed that this elliptic curve E somehow cannot exist, and therefore I cannot expect to have solutions for this Diophantine equation. Okay, so this is what we do. Do I still have some time? 5 minutes? Okay, so well, there are some key properties which are needed. Okay, so if you know this, you can implement it on Sage or Magma. Yeah, so maybe I will stop here because then I can start something new tomorrow. Yeah. Yeah. Yeah, so there is a modular forms database. It's hosted in Warwick, right? LMFDB.org. It's yeah. So yeah. So this is a very it's got its database of many things about. So it's hosted by Cremona, right? I mean John Cremona. Yeah. 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 So this. Yeah, I don't know what is the trick, but usually what they do is that they come up with equations like, so it also depends upon the type of Diophantine equations that we are trying to solve. But, sorry? Oh, you're assuming that your E is an elliptic curve.
Why did they put x minus?
Yeah, okay, so you can put here z to the p, doesn't matter. Okay, you can put here z to the p, and then you can put here, but if you put here z to the p, then you see that that elliptic curve is a twist of this elliptic curve by -1 here. So you don't get anything new. I mean, you want to put here z to the p also, that's fine. You want?
Why like that?
Yeah, I don't know. Yeah.
If you take, it will be a elliptic curve. If you do this trick, this is a trick.
Yeah, so, okay, so the point is that you're assuming that your E is an elliptic curve. You're assuming that your discriminant is non-zero there. That's why this E is an elliptic curve. I said, but so this is non-zero. So therefore, this is an elliptic curve. Yeah, it's non-zero.
When you use the factor C4 and delta, then this is
yeah, so actually I have not used it here, but yeah. You can use it in finding like n, I think. And where else do I use it? In finding n.